Okay, so I mean this slide. In fact, we have some I mean raw data sets for faces, cars, elephants, chairs, and the idea here is just to see the difference between high-level feature maps. So it looks similar, right? It looks similar, so it could be okay for just using the same convolutional layers which has been trained for faces to identify cars, is the one which has been trained for cars to identify elephants, chairs, and so on. But if it will not work with you, you can fine-tune your feature extraction part. How can we do this? Usually in feature extraction, if you need to use it as a feature extractor, we freeze the model, right? But in this case, you don't need to freeze all layers. You can just fine-tune some layers. And this specifically, I mean, the one which is closer to those ones, I don't need to go in front or in the middle. I need to go in the bottom here, right? Correct? The one which is closer to the fully connected layers, because I need to modify this one. This one, it looks like similar, but maybe small changes. How can I make those small changes? Maybe the last convolutional layer, I can just need to retrain the last convolutional layer. In this case, we will try to modify or adapt the feature maps to my problem. So what is really being transferred from one problem to another problem? This is this one. This is the one which will be transferred from one problem to another problem, right? So we need, I mean, in convolutional, in transfer learning or in convolutional layers, we start with a kernel with some random values, and after training, we will optimize the weights of this filter, right? Multiplied by the number of feature maps, correct? So if you just see, I mean, any model, for example, we have those kernels, and those kernels, we have number of kernels. Maybe we have 96 or 24, or whatever, number of feature maps, which we need to extract. So in fact, the feature map is a result of passing the weights filter on the input image during the convolution process. So when we train a model, or when we transfer a model as a feature extractor from one problem to another problem, for example, this model has been trained on a different data sets. From these different data sets, we will get this optimized weights, right? Right? So we will apply this one to the new data set to get different feature maps. So this is what is being transferred from one problem to another problem using the transfer learning. The optimized weighted filters, or the optimized weight filters, right? So this is what is being transferred from one problem to another problem. So if this one is okay with you, if this one will help you, I mean, when you apply this one to this image, you will get those, I mean, edges and stuff like this. Maybe if you will apply it to different problem from different domain, you will get the same kind of feature maps, which will help you to solve your problem. So now we will talk also about a famous model called the VGGNet. VGGNet. It was developed in 2014 by Visual Geometry Group at Oxford University. I mean, they call it VGG from Visual Geometry Group. This model, it was developed in 2014, so the building blocks are exactly the same as those in LeNet and AlexNet, except that VGGNet is deeper. It's more deeper, in fact, with more convolutional pooling and dense layers. It's just more. There are two versions, VGG16 and VGG19. 16 means number of layers, right? I mean, if we talk about LeNet, for example, it was 5 layers. AlexNet, it's 8 layers. This one, it's 16 and 19 layers, right? There are two versions, VGG16 and VGG19. VGG16 consists of 16 weight layers, 13 convolutional layers, and 3 fully connected layers. VGG16 has a unified receptive field. So the filter size is the same, 3 times 3, 3 times 3, 3 times 3. So they have this kind of unified design. I mean, we know that, I mean, the filter size, this is the receptive field which will, scan the whole image, right? This is a receptive field. So the receptive field here, it's unified, and they use REMU as activation functions for all layers, of course, except the last fully connected layer, which is softmax. So VGG16, it's fantastic, but the input volume, it's height times width times 3. Which, it expects to get, RGB images, right? So if you are working with grayscale image, you need to convert this grayscale image from 1 channel into 3 channels. So I got this one, in fact, inspired by, because you wrote something in Blackboard. Yes, fashion MNIST. And I said, okay, we need to try this one. That's a nice data set from Maintown. So we need to apply VGG16 as a feature extractor for this fashion MNIST dataset. Fashion MNIST dataset, we have 10 classes. I guess it's we have maybe 10 classes, 50,000 images for training, 10,000 for testing, I guess. So how can we get, yes. So I just downloaded VGG16 without the classifier part, because I need to use it as a feature extractor. Right? I need to use VGG16 as a feature extractor. So I just defined a base model. This base model, just base model, this is the base model, correct? You can apply it directly, by the way. But in case of VGG16, it has 1,000 outputs. In our dataset here, we have only 10 classes. So we need to modify the classification part, classifier. We need to modify the classifier. So we will import only the feature extractor part here. So the weights, we will get the weights from ImageNet. We are happy because VGG16, it's in keras.applications. You can just import it in one line, in fact. So we define this model. Include top, we don't need to include the top. So we need to use only the feature extractor. So we need to add the part here. The input shape, this is the original one, in fact. 224 times 224 times 3. I need to modify it to this dataset, which is 32 times 32 times 3. You have some freedom, in fact, to go down, but not that much, because this one, it will be based on the size of the filter and yes.
How is it to use such a small input size in 16 layers?
Which is small, this one?
Yeah, like 32 times 32 in 16 layers.
Because maybe they are using zero padding, so they will keep the same size all time, right? Yeah. If we are using zero padding, for example. Yeah. So we will keep the same dimension of the feature maps, will be the same as the input volume. Even if it's go down, it will go down. So there are some restrictions. If you will go, for example, for 28, maybe it will not work. This is the minimum. Okay. So the minimum, it's based on this. So if you will go down, if you will start from some dimension, you need to get valid feature maps at the end. So if the size, it will go to 0, for example, or -1 or something, it will not work with you. So it will not accept it. You will get an error message. So in fact, when you are selecting this input shape, right, it's based about what you have just mentioned. Yeah. Because we have some restrictions, and we need to start with some size to end up with some feature maps, valid size of feature maps. So in the documentations of each model, they will describe it. We can go down to something. This is the minimum, in fact, for this model. This is the minimum. So, so this is the base model. We will get the weights from this ImageNet, and it has been trained using ImageNet. And as I told you, ImageNet, it's a very huge data set. It has 22,000 classes and 14 million images, right? So they have been trained on it, right? But they have been using it for classifying 1,000 objects. So we need to modify it to, in this case here, 10 objects, right? So we will import the feature extraction part, and we need to freeze the feature extraction layers. We need to freeze it because we need to train it one more time. So we need to use this one 4-layer in base model.layers, layer.trainable false. From this one, in fact, you can freeze some layers and keep other layers for training. So Hamad, your question, so you can just maybe freeze all layers except the last, because now we're using this one to freeze all layers, because we will not retrain it, right? So if you need to fine tune the model, you can just freeze all except except the last layer, for example, right? So in this case, you will modify the high-level feature maps. You will adapt it to your problem, for example. So if you use this base model.summary, you will get all information. We will open the code now. Now we will save the output of the last layer of VGG16 to be. Now I will apply all my data points will be applied here. So the input will be the input to the base model, right? The output from this model, I will apply it to fully connected layers. So I need to, because I defined this one as a model, there are some other implementations. There is a much easier way for implementing it. I will show it to you next. So I need to get the last layer output. So the last layer, it will be base model get layer. I need to get the output from this last layer. So the last output will be the last layer output, right? So I need to get the output from this model, which is the last layer output. And I will flatten it, right? And I will add 2 fully connected layers. So the number of units here will be 64, number of units here will be 10, because my data set has 10 classes. The activation here, it will be RELU, the activation here will be softmix. So this is how we build it. And after that, I will just define a new model. So the new model will be, the inputs will be the input to the base model, and the output will be this X, right? And just retrain this model using the data set which you have. So in this case, we will train only the weights of the 2 fully connected layers. If you want to make some adjustment, fine tuning, so this fine tuning will be done here. You will freeze all layers, right? Except maybe the last convolutional layer. So it will be included into those 2 fully connected layers, and it will be retrained one more time. So it's like a kind of fine tuning. In fact, we should test it, right? Oh my God.
Oh my God.
Yeah, sorry.
Yeah, it's okay.
Huh?
Turn it off.
No, it's still on.
Can you turn off your computer?
Should I turn it?
Yeah.
Can I make someone else as
disconnected from power?
You can use this.
can I make someone else as
What? I can hold it.
okay. Yes, please. Can I get
Yeah, you can get.
So Ahmed, please, if you hear me, I will switch off my computer. But maybe it's fine, right?
Yes, I can hear you. Okay.
Should I switch
Thanks.
off or just?
Ahmad Amin Lotfi.
Yes.
I should switch off. So who will continue teaching?
I think Ahmad is.
No, but maybe Mengi Pao could.
Mint.
Yes.
Yeah, he can.
He can do his
Like, yeah, yes.
Okay. Are you online, Mingtan?
Yes.
Are you? So I will make you as a co-host and. Sorry, just my computer is. It's not crashing yet.
Yes.
It's floating in water.
As soon as the water hits the electrical, it's screwed up.
It's leaking.
No, it's fine. I guess it's okay. Mingtan, we can continue. I guess.
Yeah. Lucky. Lucky.
I had a keyboard, in fact, before.
Yeah.
It was a Apple keyboard, just little coffee and it just destroy it.
Yeah. It's better design this.
Yeah?
It's better design.
Yeah, this is Razer, maybe it's.
Yeah.
Yes. So we will just continue and. So I mean, we modified. Now we have the model, and we can just retrain the model using our data set, and we need to test it also for. So this is a model because I used this summary model.summary. So we have all those layers. So the input will be 32 times 3, and we will use all convolutional layers. And this is the total number of parameters, and this is the trainable parameter, right? Those parameters, in fact, it's the parameters of the fully connected layers. Those parameters are the parameters which which is frozen. We will not train those layers. So if you want to make some changes, you can just make some changes. And I trained this model for 20 epoch with this fashion MNIST dataset. And this is how the training and validation loss and the training and validation accuracy. So this is much easier from my point of view. If you will use sequential, it will be much easier, in fact. If you want to implement it as a sequential, so it will be your transfer learning model will be just one line. So now I define a model which is sequential. We will add one layer. This model, the whole model will be one layer here. VGG16. We are not including the classifier weights coming from here. This is the input shape. We will flatten directly, right? So it's much easier now. So it's just the whole pre-trained model. Feature extractor will be just one line, and we will flatten, and after that we have another two layers, fully connected layers, dense layers, and model layer 0, trainable false. Because this is, now it's the whole model is considered as a layer, right? So we will just, we will freeze the whole model. So model layer 0, trainable equal false. But if you want to make something more complex, we need to go for the other configuration or implementation. But this one, it's much easy to build and much easy to understand. Now we will retrain the model. Of course, now it's a different model, and I run it from different. So maybe this one, it's different from the other one. It's not exactly the same because this one for the sequential model, not from the other model. If you want to go to the code, so this is the code. We import VGG16. Can anyone know why should we not use pre-processed input? Is it something which we really need to use or not?
For predicting.
For
prediction.
For prediction?
Yes.
So if we have some new data sets, we need to not for retraining.
No, not for that. But, that's the way I used it.
Yeah, in fact, we should use it. In fact, but, in some examples I used it, and some other examples I didn't use it. In fact, so we have our data set. It's called fashion MNIST. So we get it from keras.datasets using this line, and this is my data set. And the plotting, you can just plot. You can do what you want. And in fact, the original size here is 28 times 28. But we cannot use 28 times 28, and it's in grayscale. In fact, so fashion MNIST dataset, it's a grayscale. So it's 28 times 28. So the size is not fitting, and also it's one channel. It's not 3 channels. So if you want to use VGG16, we need to change this one into 3 channels. We need to increase the depth, right? So in this case, we need to do some, manipulate our data set here. So I just resize the image. I'm using, resize the image into 32 times 32. And when you resize it, we interpolate. We make some interpolation for each pixel values to just expand the image size, right? So we use this one from OpenCV. And after that, I need also to extend. I need to repeat this one. So repeat, I mean the dimension 3 times. We need to repeat the dimension 3 times. So I just have 3 copies, in fact. When I'm converting it into RGB, it's not RGB. I just have 3 copies from the same image. So the image is 3 layers, or consists of like RGB. So the depth now it's 3, not 1. If you need to use VGG16. So this is very important. So we need to fix the depth of the image. It should be the same depth. And also the size, we need to change the same size. If I selected this one, we can go for 124 times 124, but the memory here, which we have in Colab, it will not help us. I have been trying this, in fact, with Muhammad, but I mean, we cannot use, I cannot go for the same size of VGG16, which is 224 times 224. But we can go to 32 times 32. This is minimum. This is the minimum size of feature maps, or the input volume, in fact, which we can use. So if you want to check it, you just need to go to Keras.applications. In Keras.applications, there is a list of transfer learning models, which we can use. There are lots of models. You can go for each model and check the documentation of each model. I mean, there they will mention the minimum size of the input volume. So this is very, very important. So after that, now it's 32 times 32 times 3. So now it's in the correct format, which can be used by our model. This is the model which I told you. You can just build the model in this way. Here, if you want to make some readjustment for the model itself, because now we are using the base model as an input. If you want to make some changes to the model and fine-tuning it, you can do it here. If you want to, this is different. So in fact, I have here, I mean, this is the model. Trainable parameters, 14 million parameters for VGG16. If you will freeze the model, now its total number of parameters, trainable parameters is equal 0, because we freeze all model weights, model layers. We will not train the model layers, so number of trainable parameters is 0. And when I attach it to my model, so now we have only this number of parameters, 33,000. Those 33,000, in fact, it's number of weights of the fully connected layers. So in fact, it's 64 times 512 plus 64 plus 10 times 64 plus 10. So this is the number of trainable parameters. I mean, the last layer here, it's called the block 5. So if you want to play with this one, you can just try Hamad, for example. If you want to fine tune the high level features which we are getting, right? So maybe you can just, you can retrain this model. You can retrain this one, block 5 conv 3, for example. This is the last layer, last convolutional layer, which we need to test it. So I trained it using 20 epochs, and we have this response. So you have, I mean, you have the code, so you can just go to the code and try to play with it. So any question for VGG16? Any questions? Okay, so this is the confusion matrix. Maybe the confusion matrix is not the best. Maybe you need to retrain the model more time, because I mean, it's okay, but maybe it's not very, maybe the accuracy is 80% something, or 85% or something. So maybe the fourth model today, it's something called the Inception Network. Inception Network. There are also different categories and different versions of this one. This Inception was published in 2014 by a group of researchers at Google. So the main idea was to build a deeper neural network while improving utilization of computing resources inside the network. So they introduced, there's a reducer, in fact, one layer called reducer. One layer called reducer. So the Inception, this is the classical structure, in fact, which we use. So in fact, we have some inputs, convolution, pooling, convolution, pooling, for example, and after that, fully connected softmax on top, right? So this is the classical CNN feature extractor approach, how we design it. So in fact, here, they introduced something called Inception modules. They introduced something called the Inception modules, and the idea from this Inception modules is to improve the computational efficiency of your model, reduce number of computations. So just a way to improve the computational resources inside the network. So now we need to know what is the Inception module. This is the Inception module. So the Inception module is a combination of 4 layers, consists of 4 layers in parallel. And one, I mean, the first one, it's 1 times 1 convolutions. This 1 times 1 convolution, it will just reduce number of feature maps maybe it's from 200 to 64. So this one, it's very efficient, in fact. They call it a reducer layer. So the filter size here, it would be 1 times 1, right? Filter size, it will be 1 times 1, and it's just to reduce number of feature maps, maybe from 200 into 64, right? And this, it's a dimensionality reduction, and it's useful for overfitting problems, to get rid of this or to resist this overfitting problem. We have here we have convolutional layer here. It's 3 times 3. So now we will get 128 feature maps, right? This one, it's the filter size, it's 3 times 3. When we apply this one to this one, we need to extract, for example, 128 feature maps, 5 times 5 convolutions. We will need to get 32 feature maps. The idea here, we need to get the same size because we need to concatenate. We need to concatenate those feature maps together. So we need to be careful that we have the same size, the same height and width, right? Of feature maps. So this one is 32 times 32, 32 times 32, 32 times 32, 32 times 32, concatenate. So we will get 32 times 32 times 256. So they call this one, it's the inception module. So the inception module consists of 4 layers, 1 times 1 convolutional layer, 3 times 3 convolutional layer, 5 times 5, 5, 3 times 3 max pooling, right? And the outputs of those layers are concatenated into a single output volume, forming the input of the next stage. So this one, we will have some inputs here. We will create some outputs. This output will be the input to the next stage. And they will use this one maybe 2-3 times in the network. In the next, concatenate the depths of the 4 outputs to create one output volume of dimension 32 times 32 times 256. So this is the inception module. When you use this inception module in a network, we call it inception network. So what is the idea behind using this 1 times 1 convolutional layer? They call it reducer. It's used for, they call it reducer layer, for example, or bottleneck layer. So the idea here is to add 1 times 1 convolutional layer before the bigger kernels, like 3 times 3 and 5 times 5 convolutional layers, to reduce the depths, which is in turn will reduce number of operations. When we reduce number of feature maps, we are reducing the number of operations, right? So we need to take an example. Yes. So sometimes they call it dimensionality reduction layer, sometimes they call it reducer layer, bottleneck layer, whatever. So for example, we have here 32 times 32 times 200. When you apply, for example, 1 times 1 convolutional layers with 16 filters. So what will be the dimension of the output? So it will be 32 times 32 if you are using, zero padding and stuff like this. So we will keep the same dimension, but we will reduce number of feature maps from 200 into 16. Right? Now, we will apply again 5 times 5 convolution. We need to get 32 feature maps. So at the end, we will get 32 times 32 times 32. So it's just imagine how much reduction in the number of operations. If you want to apply this one directly to this one, what will happen? If we need to apply this one to this one directly, to the input volume, this input volume, how many operations? How many operations? It will be 5 times 5 times 200 times 32, correct? Plus 32. Is it correct? Maybe because we have the bias calculations also. So this is just roughly the number of operations. It will be 5 times 5 times 32 times 32 times 200, because we apply it pixel by pixel. This is the number of operations, number of multiplications, right? Number of applications, or number of public applications. So at the end, we will have 163 million operations, more than, in fact. So it's very, computationally demanding operations. But if you will use this bottleneck layer here, so this one will be the number of operations. Number of operations here, it will be 32 times 32. It will be 32 times 32 times 16 times 1 times 1 times 200, because the filter is 1 times 1. So in fact, it will be 1 times 1 times 200, correct? Times 13 times 32 times 32 times 16, correct? So it will be 3.2 million operations. Here, what is the computational cost? The computational cost here, it will be 32 times 32 times 16 times 5 times 5 times 32, right? So here it will be 13.1 millions. When we're summing it together, it will be in total 16.3 million operations, right? When we are using this bottleneck or reducer layer. But if you didn't use the reducer layer here, this one will be the number of operations. So it's like 90% reduction in calculation time, right? 90% reduction. So using this bottleneck, it's very, very efficient, and we just need to use it. So if you are building a model, for example, and you feel that it's too slow because of the number of calculations which you are doing. You can just try to use this bottleneck and test it. And the bottleneck, it's one layer with 1 times 1 filter. A number of filters or number of features should be less than this one. So if this layer, for example, you have this convolutional layer and you have here 200 feature maps, you can just add this bottleneck layer for example, 16 or 32. So in this case, we will reduce number of feature maps from this number into this number. So it will reduce a lot the number of calculations by around 90%. So this is very, very important. So a reducer layer. So the idea of the 1 times 1 convolutional layer is we preserve the spatial dimension. We have the same dimension, we have the same height and the same width of the input volume, but it changed number of channels, number of the depth. We try to minimize or reduce the depth. When implemented in moderations, you can shrink the representation size significantly without hurting performance, and they save a lot of computations. So if you apply it in a moderated way, for example, you will reduce number of computations and you will improve the performance of you will preserve also the same, dimensions, the width and the height and width of feature maps, but you will reduce the number of feature maps a lot. So this is very, very important. So if you have overfitting in your model, because I have been training some examples here at the end, and I have too much overfitting, maybe I need to use this bottleneck layer or reducer layer, for example. Yes. Okay. So the inception module, you can just improve the inception module by adding those reducer layers before each convolutional layer here. So just adding this one here, adding this one here, adding this one here. So it will help you a lot to the inception module. So this is GoogleNet architecture. So we start with input, some convolutional layer. Internet connection is unstable. So maybe this is a coffee started to work. So we have some convolutional layer. We have those, we call it inception layers, for example. We have 3 inception layers. After each inception layer, we have some max pooling, global average pooling, for example. So this is the structure of the GoogleNet. So this part, it's identical to AlexNet and LeeNet. And this one part, B, it's containing 9 inception blocks. We have here 9 inception blocks, and it's separated by 3 times the 3 max pooling layers. And finally, we have the classifier. So if you want to transfer this one, we will just import the whole inception model, excluding the top layers for classifications. And you need to add on top of it your classifier. You need to design your classifier. You need to freeze the model parameters, right? And retrain the whole model again. Do we have some questions? Yes, I cannot hear you. You are right. Ahmed. So Ahmed, he's just asking you because we cannot hear him. So I don't know, Ahmed. Can anyone try? Speaker and microphone. Hello? Can you hear me? Yes, it should be working. But you need to unmute your mic. Maybe you are muting your mic, Ahmed. Please. Unmute your mic. Please just try to unmute your mic and try to say something. Yes. Okay. So now we will go to CIFAR. I mean, I want to apply this model to this CIFAR 10. So, yes.
Could I ask a question?
Yes, please.
Regarding the assignment you gave us last time, or the task. I don't understand why it works, but it's kind of weird because if I add dropout layer after max pooling, it doesn't overfit.
But we cannot add the dropout after max pooling, right? We should add it after convolution.
Yeah, but it works for some reason. If I add it after the convolutional layer, it doesn't work. So I don't understand why it works after max pooling layer.
But dropout, it should be in, I mean, after fully connected layer, or should be after convolutional layer?
Yeah, but
it's not after convolutional layer. We don't use dropout after convolutional layer, right?
But what dropout after max pooling? Dropout after max pooling.
It works.
Yeah.
Because in max pooling we don't have any weights. So what is the function? I mean, why should we use this after the max pooling?
I don't know. I just did a mistake and it worked.
And it works?
Yeah. So I can't understand why. Like you say.
It's actually the same on my model.
The
one that I took or found on Kaggle.
So
the dropout after max pooling before the next convolutional layer. Actually.
You have no idea, in fact. We need to check it.
Yeah.
Seems like it's a common way to do it.
I will go back to it and yes. So now we need to work with CIFAR 10. So we need to use this inception model. I find also this inception version 3 in Keras.applications. So I just defined a model as a sequential, and I added inception as a layer in that model. So we have here inception. Weights also are imported by ImageNet. So this model was trained by ImageNet. I mean, when we weights equal ImageNet, it means we import the weights which has been, weights of the model which has been trained using ImageNet dataset. We don't include the top classification layers. So the shape here also, I just selected the shape 75 times 75 times 3, because this is a minimum shape for in case of inception. So in case of inception, this is the minimum. You can go up to it, but when it's up, it will be hard for me in my RAM to resize the whole images. It will crash, in fact. So when I'm using something higher than 75, I mean my collab crashes. It needs more RAM. So and I just I flatten and I added 3 dense layers. So number of units here, it's 1024, here it's 128. I added some dropout here, but the accuracy here, it's very bad. It's not very good. We have here also 10. We have here 10 classes in CFAR. We have cars, airplanes, stuff like this. So this is the total number of parameters, 24 million, and the trainable parameters now it's 2 million. So those 2 million, in fact, we got them from here. We will flatten here, multiplying it with this number of weights, this number times this number times this number, right? So those are the 2 million weights which we need to train. And I trained the model for 50 epoch, and I got this kind of confusion. So you just need to go to this code and check what was the accuracy, average accuracy of this model. So this is Inception. So if you want to import Inception, we need to import it from Keras applications.inception versions. There are lots of Inception in Keras.application. I just picked this one, in fact. So you need to know the difference between each model, because there are different versions of Inception. And I used my data here. It's a Fashion MNIST. Still using Fashion MNIST dataset. Sorry, it's not C4. So I did a mistake, in fact, in the slides. It's not C4 10. It's still Fashion MNIST. So I resized it into 75 times 75. Because the original shape, it's 28 times 20. No, the original shape, in fact, is 32 times 32 times 3. And I need to modify the original shape into 75 times 75. It's a C4, in fact. This one is C4, correct? So why here it's Fashion MNIST? Oh, I have also C4 here. Sorry. I have, okay, this is the last one which I'm using. So it's still, really, it's C4 10. Not, maybe this one comes after this one. So now it works with C4 10. So this is my model. And I trained it. So the accuracy is, maybe the accuracy, look, it's 69%, which is not good. So there are lots of space to improve. We should get accuracy not less than 97%. So we need to play with hyperparameters, maybe change the model structure and stuff like this to get better accuracy. And this is the confusion matrix. Yes. Any question for this? The difference, it's Inception module. We have those Inception layer or Inception modules. And okay.
For each layer, we apply all 3 layers of Inception.
Mm-hmm.
Like we have different convolutions, like 1 cross 1.
Yes.
So if we have
change in the model.
Yeah, if we have 1 layer of input, then before applying, like for example, we were focusing on 5 cross 5. So we have to apply before that 1 cross 1. So like before that, if you go back, can you go back? Like here, the actual convolution layer is like 5 cross 5. So before that, we include this bottleneck layer or reducer layer, 1 cross 5, 1 cross 1. And there are other like 3 cross 3, and then we have to concatenate something. So it's a little bit confusing, like how we are like using this 1 cross 1. On which basis we decided 1 cross 1? Why we didn't decided to use 3 cross 3?
Because they call it dimensional reduction layer, and it's just because we need to reduce number of calculations. They just build a very complex model, and this complex model it requires too much calculations. So one way for reducing this number of calculations is using this bottleneck layer. This bottleneck, yeah, I agree with you. You want, for example, why should we select here 200? it was possible directly to select 16, for example, right? Yes, I mean, it's, because because those hyperparameters, in fact, it's by trial and error. So they've been experimenting a lot to get those numbers. Those numbers are working fine. But now it takes too much time for training your model because number of computations is exponential, in fact. It's very huge. So one way for making it more efficient is to introduce those bottleneck layers between each convolutional layers. But those numbers, I mean, the question here, if you are online, please, I mean, the question here for Hamed, why shouldn't we just select directly this 116 instead of 200, right? So why should we use those bottleneck layers here and make it more complex, looks more complex, right? It was from the beginning, we can just say, okay, I can just select this 132. But we have a stack of convolutional layers, and the number of feature maps, they got those numbers by trial and error, lots of work, in fact, and lots of trial and error until they can come up with good numbers to give good performance. So maybe they have been testing a lot until they can achieve maybe 95%, 99% accuracy. And after that, the model really is very complex because the number of computation is huge. So now they want to make it more simple. So you can just introduce this bottleneck layers. And they said that when you introduce those reducer layer with moderate number of feature maps, you will not hurt the performance, you will not hurt the accuracy of your model, but you will improve the computational computational performance a lot, in fact. So I guess they have been testing first, and after they just agreed on a nice design, which will give us very good accuracy, they try to improve the performance of the model by introducing those reduced layers. So because as this example here, it can reduce the number of calculations by 90%. It's big, I mean, huge success, in fact. So in this case, maybe instead of training your model in 1 hour, imagine it could be trained in 10 minutes, for example, or something, each epoch, for example.
So what they do is like they concatenate the feature maps together.
Yeah, they concatenated, yes, correct. So after, I mean, the output from this inception module, in fact, it's depth concatenation, correct? So I mean, also it's by trial and error. Maybe it's some ideas. They said, okay, maybe this one will help us to get better performance, introducing this inception modules. And in this inception modules, it consists of some layers on parallel. And at the end of this module, we need to concatenate those depth into one volume, right? So maybe the volume here it's 200. From this one, we will get some number of, but the same. We need to have the same dimension of feature maps. So this one should generate. We need to be sure that we are selecting. I mean, the design here we should get the same width and height, right? And after that, we will concatenate all those depth images, so we can get one volume of feature maps. But the same size, we need to get the same size here.
Before feeding it to
the next layer. And in how many of those, it's also how many inception modules you need to, I mean, insert in your model. Maybe they did it also by trial and error, right? So different of experimentations until they can find a good, I mean, good performance, good accuracy. So for example, I mean, it's just, they have two units from this one, 5 units, 2 units, right? So they have 9, in fact, 9 modules of inception, 9 inception modules, which is really very huge. So the model is really very complex. Why it's 2, why it's 5, why here it's 2, for example? It's just by trial and error. I mean, they design it and they experiment a lot with the data. And they're just watching the accuracy. We need to get better accuracy. Maybe if it is 1 unit here, 3 units here, 1 unit here, you will get maybe 95% accuracy. If this one will be 2, 5, maybe they can reach 99% accuracy. So they just keep experimenting and by trial and error until they reach good number. It's all by trial and error. There is no rule for anything, in fact, right? So there is no rule for selecting volume, filter size, and stuff like this. So it needs too much time for working and testing and stuff like this. So, I mean, if we need to use this, GoogleNet, for example, I mean, we will just use the whole model, except the top part. We need to replace the top part with our classifier. So if you will use this one for feature extractions, we need to add a new classifier. So we will exclude the top, the classifier, and we will add our classifier according to our problem. So I used it here for CFAR10, for example. In CFAR10, we have 10 classes. The input volume should be also modified, right? And as you can see here, this is the dimension of the output. This is the output shape from the inception. So from the inception, it will be 2048 feature maps times 1 times 1. So this will be the input. You need to flatten this one, so it will be this size. And after that, you need to add your dense layers. Here I use this, I added 2 dense layers with dropout, for example. So, but the accuracy is it's less than 70%. So we need to train it more. We need to modify it. I made this example just to show you the system. But we need to make some changes, in fact, to reach maybe, because we should reach maybe minimum 97%. Because when they experimented this one in 2014, they can achieve 97% to 98%. So. The last one for today, it's this residual net. This residual neural network was developed in 2015 by a group from Microsoft research team. So they call it residual network because we have this, we have something called the escape connection, or so they introduced the novel residual module architecture with escape connections. They have something called escape connection. Escape connections are shortcuts that allow the gradient to be directly back propagated from earlier layer to a later layer, creating a shortcut path from for the gradient to flow through, solving vanishing. You know, in those deep, when we go deeper, we have a problem of vanishing gradient. One way for solving this vanishing gradient is to use this escape connection. So in fact, this is a traditional approach. We have some layers stacked together. So the output maps from one layer will be the input to the next layer, and so on. And when we go back and when we use back propagation to adjust weights, we go layer by layer, right? So the problem here, maybe the gradient at some layer will be very, very small, and it will not help us to adjust weights. One way for solving it is to use this escape connection. And this escape connection, in fact, we are just providing a path or a bridge to transfer the gradient from one layer, from an earlier layer to a later layer directly. So to improve the gradient on the next layer. So this one now we will have a direct path of the gradient from an earlier layer to a later layer, right? So now this one can see, this one will consume the outputs coming from here. So the error back propagation will go through this one anyway as normal, but also we will have another path from here to this one. So it will improve the learning performance, or using this escape connection or bridge. So this escape connection or the bridge, it will provide different paths for the gradient to improve conversions and the training. So another important benefit for escape connection also is they allow the model to learn an identity function, which means that the layer will perform at least as well as the previous layer. If we are providing the gradient from this to this one will see the same, the same gradient, in fact, similar to this one, right? So now we are feeding this one with the gradient coming in the normal way, but also when we are providing this escape connection, we will help it to perform much better because we provide more information, in fact. This is the problem in deep learning. When we go deeply, in fact, we have this problem. So imagine we have 3, 4, 5 fully connected layers or dense layers, for example. We're using error back propagation. If we are not using ReLU, for example, if we are using Gaussian or hyperbolic tangent, for example, the gradient will go down very quickly. And some layers, in fact, the gradient at some layers, it will be almost 0. So those weights will not be adjusted as we are expecting. And when we are not adjusting those weights, maybe we will keep those weights as random values. And when it's random, in fact, we will generate some feature maps as random maps. It will be just pixel values multiplied by random values, because we have the filter size, it's 9 times 9, 3 times 3, for example, and it's just weights. And imagine that those weights are random values multiplied by pixel values, applying activation. So we will get some maps, feature maps, which is just random image of random applications of weights to the original image, for example. So it will be a big problem. So one way for fixing this one and improving the performance using this skip connection. Without skip connection, this is the traditional approach which we are using today. With the skip connection, this is a novelty in this approach, using those skip connections or bridges. So in fact, the output here, I mean, we apply it here, in fact, before the activation layer. So usually, I mean, we have a filter here. This filter, we will apply this filter to the feature maps, right? We will get some numbers. Before applying those numbers to the activation, we will sum the values which we're getting here from here.
So we will have two gradients at this 1 second layer, one from this layer and one from previous layer.
Yes.
How do you do this in Keras if you want to make a RESTnet in Keras?
Yeah, I have this implementation here. So skip connection, we have a main bus. This is the main bus which we are using. And we have here skip connection. So we have convolution, and each convolution it's followed by ReLU, correct? We apply the convolutional layer, and numbers will be applied to ReLU convolution. So it will be implemented, in fact, between the convolution and ReLU. This is the main bus. We will get some values here, and we will add to it the value, short pass value from the. So if the input is X, we will get here Fx, right? So the value which will be applied to this ReLU, it will be Fx plus X. So in traditional network, convolutional layers are stacked one after each other. In RESTnet, we still stack convolutional layers as before, but we also add the original input to the output from the convolutional block. So we have the original input. We have a feature map here. We apply this convolution to a feature map, right? So we will just add, but of course it should be the same size, right? It should be the same. This is the task here. We need to be careful about the size, width and height and width of feature maps. So this is one way for implementing it, just a simple example. So I have X here. So I will just say, okay, short pass or shortcut equal X. Assign it to a new variable, for example. But remember, X, it's a feature map. So we will apply this convolutional layer. So we will apply convolutional with size F1. We need to keep the same size. So the kernel size will be the same, 3 times 3, stride will be the same, all will be the same. Correct? Because we need to get the same, dimension, the same spatial size, or right? So we need to have the same. So we will apply first this convolutional layer to X. So the input here will be X. Correct? When we apply it to X, we will get X here. We just apply X, we'll apply convolution to X, we will get X. And after that, we will apply ReLU. We will apply the activation, right? And after that, we will apply again the second convolution to the same input X, to the main bus. So we will get a value here. So this value, we will add X to X to the short pass or shortcut. So just adding here X and X shortcut, right? So now we are adding it, and this added value, we will send it to the new activation. So we have this kind of shortcut or skip connection here.
X shortcut is also before the activation of the
yes, it's a value. We just need to keep it because now we are changing all X values, so we need to keep it here in some variable.
I mean, it's from the last layer, but before the activation.
Yes, and imagine if you want to do it for 2 layers, so just increase. If you want to increase number of blocks here, you can just increase it as you want. So if you want to have this skip connection for 2 convolutions, 3 convolutions, so it's up to you.
So this add function makes it possible to have a parallel connection.
Yes, to create this kind of bridge. And So they claim that this one will improve the convergence speed and learning and the performance of your model. And they call it residual neural network. So in fact, I mean, with this kind of knowledge, we should be able to try to build our own architecture, for example, maybe mixing all those together. Maybe we have inception, we have residual. If we can mix inception with residual, maybe you can find a better solution, right? But it requires too much trial and error.
So just when we will be having two feature maps
Here at the end, no, only one.
after convolution.
Here, no, because we are summing pixel values. So imagine we have a feature map here. We have a feature map here, all the feature maps which are coming from here. We're just adding all values together, pixel wise, or how do you call it? Pixel wise? So just adding all values, summing. So at the end here, we will have one feature map. This feature map, we will send all values to our ELU to calculate. I mean,
Maybe it is useful for time series data or something, like maybe activity recognition or something.
it could be a very good idea, right?
Yeah,
Because-
we are focusing multiple frames.
Mhm.
Maybe it is good for
Mhm.
dealing in such kind of.
Yeah, it could be. It could be. We need to test it, in fact. Time series, text, because maybe this is like a kind of context or keeping some context, right? So using historical values or some old values. Mhm. So this is how you implement it. If you want to implement it maybe we can try it for simple, this residual or this escape connection. For example, we can build a simple model for MNIST dataset, for example, and we can test this. We can test this escape connection and also inception and stuff like this, right? And maybe because when we implement it in a small dataset, we can make comparisons and we can get better understanding of, I mean, the impact of those stuff. So we can really customize it for simple dataset and try it.
Is it similar to like LSTM?
Hmm?
Similar to LSTM?
Maybe Megata, we should ask this also. Is it similar to LSTM?
No.
Totally different.
Mhm.
I would
Yes. We are finishing, I mean, almost. So these are the building blocks. So ResNet, in fact, it's a series of these residual blocks that are stacked on top of each other. So this is classical CNN, which we know it. We're starting from the inputs here until we have on the top here, we have fully connected layers for classification. This is the inception. In the inception, we should have some modules from inception modules. And this is the residual. So residual, you can just imagine that it's a residual block, right? We can just add some residual blocks. It's as normal. We will stack some layers together, but we will add some residual blocks. This one will be a residual block. And we have, do you see? We can have this shortcut across number of convolutional layers. So we have here 3 convolutional layers. And we can have this, we can call it a residual block. So we need to implement a residual block and add several residual blocks into your, stack it with other convolutional layers. So how can we look? We have this one from here, maybe you can add one from here. Why not? Maybe, right? Just make some changes and test it, right? So, I also, so there are 50 layers, in fact, residual net 50, it consists of 50 layers. So it's much deeper now. And therefore, it was very important to have this skip connection because it's too much deep. And we should just expect that when it's 50 layers deep, we will have vanishing gradient problem here. And therefore, we need to use those residual blocks. So if you want to use it, it's just also simple. We need to select, I use the residual net 50. We import weights from dataset image net. We are not including top, right? And the input shape will be 32 times 3. So it's expecting it to get RGB images. And we will flatten and we will use number of dense layers and model layer number 0, not trainable equal false, because we will not train it, we will not retrain it. So this is very, very simple approach for, and I applied it also to CFAR10, and we have this. So look, do you see 25 million parameters, and also to something. So this is the performance of in performance in CFAR10. So I just did it last night, in fact. So we need to spend the time fixing it because the accuracy here also, it's very, I mean, it's around 70%. So this is not a performance. I trained it for maybe 50 book or something, but maybe we need to make some changes, improvement, and try to reach 97%, 98%. It should be. So maybe we need to train it for more number of ebooks, right? I just trained it for 50 ebook, but we can try to improve it. Yes. So any questions for that part? I guess today it's very useful and it's important because we need to know the difference between different transfer learning models and how can we implement it. Difference between just use transferred learning model as feature extractor or fine tuning. This is also very important. So from my point of view, there are many ideas for today. If we need to write new papers and test different models and stuff like this, we can make a lot. So yes, any questions for you online?
Abraham, I have one question about the minimum of the input image size. You mentioned that for the VGG and also for the others, but we have a task about the AlexNet for the CRFAR10 and the 100, and the default input image size for the AlexNet is 227, but it's too large. Could you tell us about the minimum size of the input shape for the AlexNet?
Yeah. So the minimum size you will get it from the documentation of each model. So you have this Keras.applications. You have a table. In fact, if you can go to Keras.applications, there is a table of all models, and there is a documentation for each model. What is the minimum size? But how can we decide the minimum size? It's according to the model structure, because we start with some volume size and we need to end up with some size. If you will start with a different one, which will make problems later on because we are applying padding, maybe no padding, stuff like this. We're applying some filter size. So if you select a size which will lead us to how do you call it? To non-realistic, for example, or feature map, it will make a problem. It will give you a warning. It will not run. In fact, it will give you a problem. So because imagine that we have input volume and we apply filter size, we apply max pooling, average pooling, and so on. So we are going down to some size. For example, maybe we are going down to a feature map of size 1 times 1 times 120. So to achieve this 1 times 1 times 120, you need to start with minimum size of input volume. If you will select a different one, maybe it will make a problem later on because we are applying all those convolutional layers. So you need to be careful. But so how they select the minimum size? It's based on those stages, because this input volume will go through different cycles or different layers, and we need to reach some specific feature map size. So if the size which we will start with will make a problem, it will make a problem. So they said, okay, we need to start with some minimum values. But if you want to get those minimum values, you need to go to this Keras.applications, check the model which you want to import, and then check the minimum size. Because I had a problem, for example, even working with MNIST or CFAR10, for example, or 100, sometimes I need to resize it to a much bigger size. When the size is much bigger, it will take more memory, right? And I'm not saving it to a file, I'm just doing it in the RAM. So a problem, in fact, it crashes. So when I select a smaller one, it's much easier to handle in the memory which we have in Colab here. But if I will go for example, we use the here ResNet, for example, it says 32 times 32. This is very good for my memory. So I can resize the images in my memory, and I can train my model and test my model. But if I will go to much bigger, because you can go for much bigger size. When it's much bigger, you need more memory. It crashes in my computer. And I had this problem, and I discussed it with Mohammed Saad 2 weeks ago, because I have been also trying this VGG 16, and I tried to go for, I guess, 128 times 128. So the memory which we have in Colab, it was not helping me. In fact, it was crashing, and I couldn't prepare the data for my model. So so if you have a problem in memory, you need to go for the minimum size, minimum accepted size for that model. This size, it's decided based on different stages, because in different stages we apply many different operators. We apply filter size, we apply max pooling, we apply all those stages. So at the end, we should get some specific feature map, high level feature map size. So imagine it's 120 times 1 times 1, for example. So if you will start with much less size, you will not be able to get this one. So you will get some error. So they decided this minimum size, minimum accepted size, based on those steps, right? Because this is the minimum one, which will give you reasonable feature maps at the end, right? So this is the task here. So if you will go to keras.applications, you will have all information about all those models. But AlexNet, you talk about AlexNet. How did you work with AlexNet? How did you get it? Can you get it from keras.applications?
I found that the AlexNet is not included in the Keras, but the VGG, like others exist. So I only found the code from the PyTorch. So this confused me that I failed to find the minimum, as you said, the input image size for the AlexNet.
So just maybe if you will try different sizes, all sizes will be working with you. And when you are below the minimum, you will get an error message if there is no documentation for it.
Yeah, I also tried some size. For example, the 60 times 60. It will pops out some errors. Maybe some inside the. So it's,
maybe it crashes because maybe you need to do it like you need to make it image by image and save it in the memory in the hard drive, for example, in a folder, so you can free space for other operations. But if you will do it maybe you need to decide a batch size. You can do it batch by batch, for example. In this case, it will work. So you need to do it batch by batch and store it in maybe in a folder, right? So in this case, you will be able to convert all images. But in my case, for example, I have been trying the whole data set one time. So when you select the size much bigger, the memory crashes because I don't have enough space, and the RAM memory is not big enough to handle the whole data set at one time. So maybe one way for solving it is to select small batch size, and do it batch by batch. Maybe in this case it will be much better. But I have a problem working with files and stuff like this, so I just prefer to do it one time. So when you select the minimum size, it works with me. So maybe the accuracy is not good here, 70%, because I'm just using 32 times 32. Maybe if we can go larger, it will be better. Maybe also the interpolation, because I'm using some interpolation, because you need to resize the image, right? It's 28 times 28, and I want to resize it to, for example, 32 or 64 times 64. So the interpolation also approach, maybe it has some impact. Correct? So, yes. Any other questions?
That means minimum is not fixed. We can use.
No, minimum is fixed for the model. You cannot go below it.
No.
Because if you will go below it, it will make a problem for the feature maps, the generated feature maps.
Not below, above it.
Above it, you can go above it. Yes. But when you go above it, you need because you need to resize the data set, right? Maybe
I think you have to keep a ratio. If you extend or make your model larger, the input larger, and you need to like have the times of, let's say, 32, 64, and so on. I'm not sure. Or can you just take an arbitrary number that is higher?
I just need to be above this minimum size. So I'm just using the minimum because when I go a little bit larger, even larger, it crashes the memory in my Colab. Because I mean the memory which we have here, maybe it's 8 GB or 4 GB, I guess, which is very, very small. 12 GB, I don't know how much memory we have.
It doesn't use all the memory. It just assigns you something automatically. So
yes,
you don't get the best.
But you have maximum value. When you above this maximum value, it crashes. So I'm just it's a problem here when I try to resize my data set at once in one step. For example, in XTrain is much larger. So it's 50,000 images. just imagine 50,000 images times 28 times 28 times 32 bits. So it takes too much memory. So it crashes, in fact, my memory. So when you go for larger size, because when larger size, it means larger memory, right? So, yes, okay. So thank you very much for this part. I will close here, and Mingita, we will take maybe some 10 minutes break or 5 minutes, and after that, Mingita, we will introduce RNN for us. Maybe he will introduce it today. Maybe we will lead you also another time to give us more details and more examples. You have.